So today we're going to move through Chapter 1, Forces, Maintaining Equilibrium or Changing Motion. So we have several objectives to accomplish for this chapter, such as define force, classify forces, define friction force, define weight, determine the resultant of two or more forces, resolve a force into component forces acting at right angles to each other, determine whether an object is in static equilibrium if the forces acting on the object are known, and determine an unknown force acting on an object if all the other forces acting on the object are known and the object is in static equilibrium. Forces are important for motion because they really enable us to start moving, stop moving, and change directions. Forces are also important even if we aren't moving. We tend to manipulate forces acting on us to maintain our balance in stationary positions. To complete a biomechanical analysis of human movement, we need a basic understanding of a human movement. We need a basic understanding of forces, how to add them to produce a resultant force, how to resolve forces into component forces, and how forces must act to maintain equilibrium. So a force is a push or a pull, and forces always come in pairs. The force exerted by one object on another is matched by an equal but oppositely directed force exerted by the second object on the first. This is referred to as action and reaction. A force is also something that accelerates or deforms an object. Mechanically speaking, something accelerates when it starts, stops, speeds up, slows down, or changes direction. So, a force is something that can cause an object to start, stop, speed up, slow down, or change direction. Many of you may be familiar with force being measured in foot-pounds. However, the SI unit of measurement in biomechanics is the Newton, named after Isaac Newton. 1 Newton of force is defined as the force required to accelerate 1 kilogram mass, 1 meter per second square. 1 Newton of force is equal to 0.225 pounds of force. 1 ripe apple weighs about 1 Newton. This might be an easy way to remember that. Some of the other important characteristics of force are its point of application, its direction, which is the line of action, and its sense, whether it pushes or pulls along this line. A force is what is known as a vector quantity. A vector is a mathematical representation of anything that is defined by its size or magnitude and its direction. The easy way to represent a force or any vector is to use an arrow. The length of the arrow indicates the size of the force. The shaft of the arrow indicates its line of application. The arrowhead indicates its sense or direction along that line of application. And one of the arrow's ends indicates the point of application of the force. So we're now going to move into classifying internal and external forces. Internal forces are forces that act with the object or system whose motion is being investigated. Remember, forces come in pairs, action and reaction. With internal forces, the action and reaction forces act on different parts of the system or the body. Each of these forces may affect the part of the body it acts on, but the two forces do not affect the motion of the whole body because the forces act in opposition. When we think about sport biomechanics, we are mostly concerned with the athlete's body and the implements manipulated by the athlete, hence the example of the shot putter. If you consider how the human body functions during movement, you may think about how muscles pull on tendons, which then pull on bones in order to cause movement. If pulling forces act on the ends of an internal structure, such as muscles, tendons, and bones, the internal pulling forces are referred to as tensile forces, and the structure is under tension. If pushing forces act on the ends of an internal structure, the internal pushing forces are referred to as comprehensive forces, and the structure is under compression. If the forces acting on the internal structure are greater than the internal forces the structure can withstand, the structure fails and breaks. Structural failure in the body occurs when muscles pull, tendons rupture, ligaments tear, and bones break. It's important to note that internal forces cannot produce any changes in the body's center of mass. The body is able to change its motion only if it can push or pull against some external object. So, what might be an external object that we use daily to make changes in our center of mass? And a great example would be the ground that we walk on. Let's consider external forces now. External forces are those that act on an object as a result of its interaction with the environment surrounding it. We can further classify external forces as contact or non-contact. However, most of the forces we think about are contact forces. Contact forces occur when objects are touching each other. Non-contact forces are forces that occur if the objects are not touching each other. Examples of non-contact forces would include the gravitational attraction of the Earth, magnetic forces, and electrical forces. With regards to sport and exercise, the only non-contact force we are concerned with is gravity. The force of gravity acting on an object is defined as the weight of the object. So when someone asks you how much you weigh, that is really an investigation of gravity acting on your body's mass, accelerating your body towards Earth. Scientists have precisely measured the acceleration for various masses at various locations around the Earth, which appears to be about 9.81 meters per second squared downward, no matter how large or small the object is. On Earth, mass is measured in kilograms and weight is measured in newtons. Kilograms and newtons are proportional to each other by a factor of 9.81. Thus, the weight of an object in newtons is its mass in kilograms times the acceleration due to gravity. Contact forces that occur between two objects in contact with each other are two objects in contact with each other. The most important contact force in sport occur between solid objects such as the athlete and some other object. To jump up in the air, you must be in contact with the ground and push down on it. The reaction force from the ground pushes up on you and accelerates you up into the air. Moreover, to accelerate yourself forward and upward as you take a running step, you must be in contact with the ground and push backward and downward against it. The reaction force from the ground pushes forward and upward against you and accelerates you forward and upward. Contact forces can be resolved into parts or components. The component of force that acts perpendicular to the surfaces of the objects in contact and the component of force that acts parallel to the surfaces in contact. We call the first component of contact force a normal contact force or normal reaction force, where normal refers to the fact that the line of action of this force is perpendicular to the surfaces in contact. The second component of the contact force is called friction. The line of action of friction is parallel to the two surfaces in contact and opposes motion or sliding between the surfaces. Let's try an experiment in order to better understand the friction. If you place a book on a flat horizontal surface such as a desk or a table, and then push it sideways against the book, and then push sideways against the book and feel how much force you can exert before the book begins to move. What force resists the force that you exert on the book and prevents the book from sliding? The resistance force is static friction, which is exerted on the book by the table or desk. If the book doesn't slide, then the static friction force acting on the book is the same size as the force you exert on the book. What happens if you place another book on top of the original? As you add books to the pile, the magnitude or the size of force you exert before the books slide becomes bigger, and so does the static force. This graph is depicting the changes seen in force application, which results in overcoming the static friction force, resulting in dynamic friction or kinetic friction. You will see the vertical axis represents the friction resistance in newtons, and the horizontal axis represents the applied force in newtons. The static friction line is representative of equal application of force to the static friction. The threshold of motion is the point in which applied force overcame static friction force. So what else affects friction? What about surface area? What happens if you try to push the book across the desk if it is standing on end? With the different orientation of the book standing on end, the surface area in contact between the book and the table varied dramatically, but friction did not change noticeably. Dry friction, both static and dynamic, is not affected by the surface area in contact. If, however, we were to press these two surfaces together, the interactions of the molecules would be greater and friction would increase. If the force pushing the surfaces together remains the same, with the greater surface area in contact, this force is spread over a greater area and the pressure between the surfaces will be less. Thus, the individual forces pushing each of the molecules together at the contact surfaces will be smaller, decreasing the interactions between the molecules and decreasing the friction. So, to summarize, the increase in surface area increases the number of molecular interactions, but the decrease in pressure decreases the magnitude of these interactions. Friction is affected by the size of the normal contact force, but is unaffected by the area in contact. Additionally, it is always easier to keep something moving than to try to get it to move at the start. Thus, static friction is larger than dynamic friction. While surface area does not affect friction, the type of material between the surfaces in contact will affect static and dynamic friction. Two hard, smooth surfaces have less friction than two rough, soft surfaces. Friction is proportional to the normal contact force pushing the two forces together. Lastly, the coefficient of friction is a number that counts for the different effects that materials have on friction. It is the ratio of friction force to normal contact force. To briefly review, we use an arrow depicted by the length of the shaft, the magnitude of force, how the line is oriented, known as the line of application, and the direction the arrow points, the direction of action, to describe a force. Forces are then added using the process of vector addition. The result of vector addition of two or more forces is called a resultant force. Vector addition can be simple because all the forces are acting along the same line, or collinear forces. Collinear forces are forces that have the same line of action. It is important to note that even though they have the same line of action, they may not be acting in the same direction or in opposite directions of each other, similar to the tug-of-war example provided on the slide. Your team is pulling to the right with 100 newtons, 200 newtons, and 400 newtons of force. In order to determine the total amount of force your team is pulling with, we can add all the force values together, knowing that they are occurring along the same line of action. Thus, 100 newtons plus 200 newtons plus 400 newtons equals 700 newtons. Since your team is pulling to the right, let's assign a positive value to it. It is important to remember that with force, a positive or negative value is an indication of direction, rather than thinking a negative force is being applied. The other team is pulling to the left with 200 newtons, 200 newtons, and 200 newtons of force. As we did prior, we simply add these values together because they are acting along the same line. 200 newtons plus 200 newtons plus 200 newtons equals 600 newtons. Since this team is pulling in the opposite direction, let's assign a negative value to that force direction. So what is the resultant force acting on the rope as a result of your team pulling to the right and the opposing team pulling to the left? 700 newtons minus 600 newtons equals a positive 100 newtons, or 100 newtons towards the right. In the tug-of-war photo, the same is true. However, all the forces have already been added together. In this example, Team A is pulling to the left with 1,000 newtons of force. For simplicity's sake, let's say pulling in the left direction is assigned a negative value. Team B is pulling to the right direction with 800 newtons of force, a positive value. The resultant force here would then be 800 newtons minus 1,000 newtons equals negative 200 newtons, or 200 newtons into the left direction. We could say then that Team A is winning, or might win, based on these force application values. If forces do not act along the same line but do act through the same point, the forces are concurrent forces. Let's consider a situation in which the external forces are not collinear but are concurrent. A gymnast jumps up and grasps the high bar in preparation for his routine. His coach applies external forces both in front of and behind him in order to stop his body from swinging. As the image indicates, the external force applied from the front is 20 newtons, 30 newtons applied in the posterior, and an upward vertical reaction force of 500 newtons is exerted by the bar onto the gymnast's hands. Let's first determine how large the force of gravity acting on the gymnast is. If you remember, we determine weight in newtons by multiplying mass, in this case 50 kilograms, by acceleration due to gravity, 9.81 meters per second squared. Thus, W equals 50 kilograms times 9.81 meters per second squared. Weight is equal to 490.5 kilograms meter per second squared. And for purposes of this example, we will just round up to 500 newtons as shown in the image. This weight is a downward force of 500 newtons. And considering this, it makes sense why not everyone can do pull-ups. Let's begin to determine what the resultant force is from these concurrent forces. Just as we did with collinear forces, we can represent each force graphically with an arrow, scaling the length of the arrow to represent the magnitude of force, orienting the arrow to show its line of application, and using an arrowhead to show its sense or direction. The first figure is a graphic representation of all forces acting on the gymnast. You will notice there is a gap in the downward weight force of 500 newtons and the force applied in the front of 20 newtons. Instead of describing the resultant force as upward and slightly to the left, we can estimate the angle from the vertical at approximately 11 degrees from vertical. Just to clarify, this is just an estimation. To make things easy, let's consider the horizontal and vertical forces separately and determine what the horizontal resultant force is and what the vertical resultant force is. As we did earlier, let's arbitrarily assign a positive value to all forces acting to the right and a negative value to all forces acting to the left. Therefore, mathematically, we have 20 newtons plus negative 30 newtons equals negative 10 newtons. The negative sign associated with this force indicates that it acts to the left. The resultant horizontal force is 10 newtons acting to the left. With regards to the vertical force, mathematically, we have negative 500 newtons plus 550 newtons equals positive 50 newtons. The positive sign associated with this force indicates that it acts in an upward direction. The resultant vertical force is 50 newtons acting upward. In order to determine the resultant of the horizontal and vertical forces, we must use the Pythagorean theorem. Take a closer look at the shape created by the three forces in the last image on the slide. It's a triangle. In fact, it's a right triangle. One of the angles in the triangle is a 90-degree angle. The 90-degree angle is formed between the sides of the triangle representing the horizontal force and the vertical resultant force. There are special relationships among the sides of a right triangle. One of these relates to the lengths of the two sides that make the right angle to the length of the side opposite the right angle. If A and B represent the two sides that make up the right angle and C represents the hypotenuse, or the side opposite of the right angle, then A squared plus B squared equals C squared. For our force triangle, we can substitute 10 newtons for side A and 50 newtons for side B, and then solve for C, which represents the resultant force. We then find a resultant force of 51 newtons. Besides the Pythagorean theorem, there are other relationships between the sides and angles of a right triangle. If we know the lengths of any two sides of a right triangle, we can determine the length of the other side and the size of the angle between the sides as well. Conversely, if we know the length of one of the angles other than the right angle, we can determine the lengths of the other sides and measurement of the other angle using trigonometry. Trigonometry tells us that a ratio exists among the lengths of the sides of the right triangles that have similar angles. These relationships can be expressed as ratios of one side to another for each size of angle that may exist between two sides of a right triangle. These relationships are referred to as sine, cosine, and tangent, and are used to determine the length of an unknown side of a right triangle if the length of the other side is known and one of the two angles other than the 90-degree angle is known. Any modern scientific calculator includes functions for sine, cosine, and tangent. An easy technique for remembering these relationships is SOHCAHTOA, or some of his children are having trouble over algebra, where the SOH or so indicates the opposite side over the hypotenuse. CAH indicates the adjacent side over the hypotenuse, and TOA or TOA indicates the opposite side over the adjacent. If the sides of the right triangle are known, then the inverse of the trigonometric function is used to complete the angle. The arcsine, arccosine, and arctangent functions are used to compute one of the angles in a right triangle if the lengths of any two sides are known. Let's go back to the resultant forces acting on the gymnast. We use the Pythagorean theorem to compute the size of the resultant force, 51 newtons. But in which direction is it acting? Let's determine the angle between the 51 Newton resultant force, or the hypotenuse of the triangle, and the 10 Newton horizontal force, making up the adjacent side. The 50 Newton vertical force is the side opposite the angle. To determine the angle, we use inverse of the tangent function, or the arctangent. Look for this function on your calculator as tan -1. Therefore, arctan, 50 newtons, divided by 10 newtons, equals arctan 5, or 78.7 degrees. The other angles in the triangle add up to 180 degrees. In a right triangle, one angle is 90 degrees, so the sum of the other two angles is 90 degrees. The other angle in this case is thus 11.3 degrees. This is pretty close to the value we arrived at earlier using the graphical method when we measured the angle. What if the external forces acting on the object are not collinear and do not act in a vertical or horizontal direction? Consider the forces acting on a shot during the putting action. Imagine that at the instant shown, the athlete exerts a 100 Newton force on the shot at an angle of 60 degrees above horizontal. The mass of the shot is 4 kilograms. What is the net force acting on the shot? We then use the formula W equals mg, which would be 4 kilograms times 9.81 meters per second squared, which is equal to 39.24 newtons. Now we can determine the net external force by graphically adding the estimated 40 newtons weight of the shot to the 100 Newton force exerted by the athlete. While we could just measure the resultant force and receive an estimate of 68 newtons, this is a graphical method for determining resultants. If we were to measure each of the vertical and horizontal components, we would arrive at approximately 50 newtons for the horizontal component and 87 newtons for the vertical. Because the weight of the shot acts as a negative downward force, in order to truly determine the vertical force, we need to take into consideration both positive and negative forces. Thus, negative 40 newtons plus 87 newtons equals positive 47 newton acting in the upward direction. We also still have the 50 newtons of horizontal force exerted by the athlete. If we add this to the 47 Newton vertical force using the Pythagorean theorem, we get a squared plus b squared equals c squared, or 50 newtons plus 47 newtons equals c squared, or a total of 4,709 newtons squared, and reduced down to c equals 68.6 newtons. In this problem, we actually resolved a force into its components, the vertical and horizontal forces, added these components two other forces along the same lines, which would be the downward force of the shot and the upward force of the athlete's exertion, and then added the resultant component forces back together to find the resultant force. The process of determining what two force components add together to make a resultant force is called force resolution. We resolve the force into its components. While we solve the problem backward, we resolved the force into its components. While we solve the problem backward, we need another method for solving this problem aside from a graphical one. Besides the Pythagorean theorem, there are other relationships between the sides and the angles of the right triangle. Some of these relationships can be described by the sine, cosine, and tangent functions. Let's see if we can use any of these relationships to resolve the 100 Newton force that the shot putter exerts on the shot into horizontal and vertical components. First, draw the 100 Newton force as an arrow acting upward and to the right 60 degrees above horizontal. Draw a box around this force so that the sides of the box are horizontal or vertical, and the 100 Newton runs diagonally through the box corner to corner. The 100 Newton force is the hypotenuse of this right triangle. The horizontal side of this triangle is the side adjacent to the 60-degree angle. The length of this side can be found by using the cosine. As shown in the slide, use a scientific calculator to determine the horizontal component of the 100 Newton force. The side of the triangle opposite the 60-degree angle represents the vertical component of the 100 Newton force. We can find the length of this side by using the sine function. Again, using your scientific calculator and the formula on the slide, please determine the vertical component of the 100 Newton force. We can now determine the net force acting on the shot by adding up all the horizontal forces to get the resultant horizontal force, and then adding up all the vertical forces to get the resultant vertical force. The only horizontal force acting on the shot is the horizontal component of the 100 newtons. This resultant force is thus 50 newtons. Two vertical forces act on the shot: the weight of the shot acting downward, or 40 newtons, and the 86.6 Newton upward vertical component of the 100 Newton force. If we add these two forces, we get a resultant force of 46.6 newtons acting upward. Now, using the Pythagorean theorem, we can find the net force acting on the shot. 50 newtons squared plus 46.6 newtons squared equals c squared, or 2,500 newtons squared plus 2,172 newtons squared equals c squared, or c equals 68.4 newtons. To complete this problem, we need to know the direction of this net external force. We can use a trigonometric relationship to determine the angle this net force makes with the horizontal. The force triangle is made up of the 46.6 Newton upward force, which is the opposite side, the 50 Newton horizontal force, or the adjacent side, and the resultant of these two forces, the net force of 68.4 newtons, or the hypotenuse. Because we are looking for an angle using component and resultant force values, we need to use the inverse or arctan function. The net external force acting on the shot is a force of 68.4 newtons, acting forward and upward at an angle of 43 degrees. So far, these techniques will be useful for an analysis of an object that is at rest or moving with constant velocity or has zero acceleration. In each of these cases, the external forces acting on the object are in equilibrium, and they result in a net force of zero. If the net force wasn't zero, the object would be accelerating as a result of these forces. If the object is at rest, the forces are in equilibrium, and the object is described as being in a state of equilibrium. Let's try our hand at free body diagrams. Take the example shown on the slide. A woman standing still on the ice. The woman's mass is 50 kilograms. What external forces are acting on her? One force we know acts on the woman is the force of gravity, which is the woman's weight. We can indicate that force is drawing that force by drawing an arrow pointing downward through the woman's center of gravity. Is weight the only force acting on the woman? If it is, then the woman should be accelerating downward 9.81 meters per second squared as a result of this force. However, because she isn't, and because she is still, we know there is another force working to cancel out the effects of gravity. Earlier we talked about how two objects that touch each other may exert forces on each other. Since the woman's skates are touching the ice, she is exerting a force onto the ice. The ice is exerting a force on the woman as well. This is the reaction force from the ice. As represented on the slide, this force could be drawn with an arrow pointing upward, whose arrowhead is just contacting the skates. Any points where the skater touches something external to her are places where external forces may be acting. This is shown in the second image above. This type of drawing is called a free body diagram, and it is a mechanical representation. In a free body diagram, only the object in question is drawn along with all the external forces acting on it. If an object is not moving, it is in static equilibrium. Therefore, we could say the ice skater is in static equilibrium because she was not accelerating and standing still on the ice. As a reminder, in static equilibrium, acceleration is zero, and the sum of all external forces acting on the object is zero. Mathematically, the situation can be described with the equation, the sum of F equaling 0. This represents the net external force, or the resultant of the external forces, or the vector sum of the external forces. If the only forces acting are collinear forces, as is in the situation with the ice skater, we find the vector sum of the external forces by adding them algebraically. But the senses, or direction, of the forces must be taken into account. As we see from the image on the slide, there is an upward reaction force that the ice exerts on the skater. We will give this force a positive value. However, we don't know how large that force is yet. That's what we would like to find out. We do know that the skater's mass is 50 kilograms, so we could determine the downward force of gravity with W equals mg, or 50 kilograms times negative 9.81 meters per second squared, or negative 500 newtons. Now that we know the force of gravity, we can write the equilibrium equation for the skater. So the sum of F equals R plus negative 500 newtons equals R minus 500 newtons, or 0, where R represents the reaction force from the ice. Since the skater is in static equilibrium, we know that the reaction force is equal, but acting in an opposing direction to the force of gravity. Hence, since the force of gravity is roughly negative 500 newtons, we know that the reaction force must also be 500 newtons, but in the upward and positive direction. Finally, let's consider the case where there is more than just the forces of weight and reaction force. The image on the slide is of a weightlifter holding a barbell above his head. There are three external forces acting on this weightlifter. 1, the reaction force from the floor acting upward on the athlete's feet. 2, the weight of the athlete acting downward through the athlete's center of gravity. And 3, the reaction force from the barbell acting downward on the athlete's hands. With only one equilibrium equation, only one unknown force can be determined, and in this situation we have two unknown forces, the reaction force from the floor and the reaction force from the barbell. Therefore, another equation must be used to determine the other unknown force, the reaction force from the barbell. The weight of the barbell is equal to 100 kilograms times negative 9.81 meters per second square, which is roughly negative 1,000 newtons. We can then use the equilibrium equation to determine the reaction force exerted by the hands on the barbell. The sum of F is equal to R plus negative 1,000 newtons is equal to R minus 1,000 newtons, or 0. R is equal to positive 1,000 newtons. The reaction force from the hands is 1,000 newtons force acting upward on the barbell. The force exerted by the hands on the barbell is equal in magnitude but opposite in direction to the force exerted by the barbell on the hands. Since the force exerted by the hands on the barbell is 1,000 newtons acting upward, the reaction force exerted by the barbell on the hands must be a reaction force of 1,000 newtons acting downward. Now we can solve for the reaction force from the floor. The weightlifter's mass is 80 kilograms. Once again, we can use the equilibrium equation to determine the reaction force from the floor. Therefore, the sum of F, or force, is equal to R plus negative 1,000 newtons plus negative 800 newtons is equal to positive 1,800 newtons. The reaction force from the floor is 1,800 newtons force acting upward on the weightlifter's feet.